Hi, good morning, folks. Today we're going to continue on with simple harmonic motion. So what are we going to start with? Uh, we're going to start off by comparing graphs of simple harmonic motion. That's kind of where we left off last time. I did a quick review of sinusoidal motion and sine functions, and I showed you quickly a graph that looked something like this, and I promised I'd get to it next time. So today we're going to get to that. What else are we going to do? We're going to talk about energy in simple harmonic motion. That's pretty quick, pretty straightforward, but it's something that AP wants you to be aware of and be able to articulate. Then we're going to see a couple of equations that go with simple harmonic motion, one involving springs and one involving pendulums. And then finally, we're going to look, if we have time, on how these equations change as you change variables within them. Okay, so let's start off. Okay, so simple harmonic motion is closely related to sine waves or sinusoidal forms. So here we have three graphs. We have a position versus time graph. This is for an oscillating object. Velocity versus time, and acceleration versus time, and they are all related to each other. So to help make this work, it will help if we have a visual representation here. So we have a weight oscillating up and down on a spring. And so what we're going to do is see how these graphs relate to this motion here. So let's look at the top one first. You know what? I'm just going to remove these. Remove these graphs here, and we'll reconstruct them so we can see what we got. All right. So let's look at the position versus time first. So we arbitrarily just start this graph someplace in the cycle, and we're going to start it when the weight is at the top. So it is at the max deflection in the upward direction. So that's why we begin it up here at the top. Let's see, I'm going to hide this, and we'll do a crayon, because why not a crayon? There we go. So at the start of the cycle, the weight is at the top. As time passes, when we're 1/4 of the way through the cycle, the weight is halfway through its motion and on its way down. So that's where we are here. Then halfway through the cycle, the weight gets all the way to the bottom. Then it comes back up and returns to its starting position. Great. Now, how about the velocity? So when the cycle begins, again, the cycle is beginning when the weight is at the top. Well, when the weight is at the top, it's not moving. It's gotten as high as we can. Its velocity has stopped just for an instant before it starts back down again. So initially, its velocity is 0. So it starts here at 0. Now, as it begins, it is moving in the downward direction. So it's moving in a negative direction. And 1/4 of the cycle, it's halfway through its motion. Its position is at the neutral position and is moving downward as fast as it possibly can. So its velocity is a max negative value. Then it slows down, and when it gets to the bottom, it is stopped. So it's continually moving downward, faster and faster and faster, and then it's slowing down. It's still moving downward, but not as fast. And then when it gets to the bottom, then it gets to 0 velocity. And then it comes back up, and it goes faster and faster and faster in upward direction until it passes through the neutral position. This is the neutral position. And that's going at its maximum speed upward. And then it slows, 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 and it stops when it gets to the top again. Then finally, the acceleration. This is the last one we want to look at. When it's the weight is at the top, it's basically in free fall at that moment, and the spring is not holding it back at all. So it is able to fall in the downward direction at its maximum possible acceleration. So that's why we have the acceleration starting off as negative, and then as the string is stretched, it slows down, or it increases a counterforce, which slows down the downward descent of the mass. So the downward acceleration is getting less and less and less until it gets to the neutral position. And when the weight gets to the neutral position right there, now the spring is stretched slightly, So the spring is trying to slow down the weight, and now you have a positive acceleration. The motion is still negative. The motion is still going downward, but the acceleration is upward because the change of the velocity is in the upward direction. It is slowing down as it descends. When it gets to the bottom, when the position is at the minimum, the position of the mass is at the bottom here, then the acceleration is maximum in the upward because the spring is stretched as much as it can be. It's applying the max force upward, and so we have the max upward velocity. Then as the weight comes up, the acceleration declines until it passes the neutral position, and then there's no acceleration on it at all as it passes the neutral position, and then gravity is starting to win, and it's causing a downward acceleration until it returns back to the starting position. Okay, so these are all related. Now, if we want to go all calculus on this, what we can say is that each graph is a derivative of the graph above it. What does that mean? Well, it means that the velocity graph is a graph of the slope of the position graph. Okay, so when we begin here, it has the position graph has just kind of come over the top. So it's basically level right at the top. The slope of this graph is horizontal at the start of it. So that means that the slope of this graph is 0. The velocity graph shows is 0, which is the slope of the position graph at this point. Now, the graph of the position, the green graph here, has the max negative slope at this point when it passes through the 1/4 cycle. And the velocity graph reflects that. The velocity has a max negative value where the position graph has a max negative slope. Now, when we get to the bottom of the cycle, the weight is as low as it can go. The slope of the position graph, again, is level, and the velocity graph passes through 0. We come over here to 3/4 of the cycle. Now the position graph has a max positive slope, and the velocity graph has a max positive value. And then we complete the cycle by the slope of the position graph is level, the slope is 0, and the velocity is 0 at this point. So interestingly enough, the velocity graph is also a graph of the slope of the position graph at each point during the cycle. Now the acceleration graph is the derivative of the velocity graph. So the slope of the velocity is at max negative value right here at the start, and the acceleration is at a max negative value right here at the start. The velocity, when we get through 1/4 of the cycle, the change in velocity is 0, so the slope of the velocity graph here is level, it is 0, and the acceleration there is 0, and so on as we go through the graph. So the acceleration graph is also a graph of the slope of the velocity graph as we go through. A little calculus preview there for you, but you can do it just by looking at the graphs, and AP may want you to do that. That's kind of in the gray area of what they may want you to do and may not want you to do. Now, these crayon scribblings that I made were pretty messy, so let me show you that again in a neater form, and there it is. That's a much smoother one when I do it on the board with the calligraphic pen. Anyway, there we are. Okay, so now let's talk about energy in simple harmonic motion. It's a fairly simple thing, but AP wants you to be aware of it and know what it looks like. So here we go. So what we're talking about here is we're graphing potential energy and kinetic energy as we go through a cycle of simple harmonic motion. Now this graph, and it's easiest to understand if we're envisioning an oscillator on a horizontal spring like this. So this is the same graphic we used before, and this came out of your book. We have a spring. This is the neutral position here at B. This is the relaxed state of the spring, and that's where the mass would be if there was no energy in the system whatsoever. If we stretch the spring, then the mass comes off to this side. We have a positive amplitude. We let it go. It swings through slides through the neutral position, and then compresses the spring and stops over here and just oscillates back and forth forever if there's no friction. Okay, and that's the system that we have here. So we're going to start off with our block at a max negative amplitude. So the minus A means a max negative amplitude, which is basically position C here, where it's pulled all the way to the left, is pushed all the way to the left as far as it can go. Now, when it's at that position, the block is stopped. It has the spring compressed as much as it can go, and the spring has managed to stop the block. So there is zero kinetic energy. The red line is the kinetic energy. At this point, there is zero kinetic energy, and all of the energy is in the form of potential energy in the compressed spring. Now, as we go through a cycle and pass toward the neutral position here, when the displacement gets to neutral, that means that the spring is completely relaxed and it's not storing any energy at all. So the potential energy in the spring is zero as we pass through the neutral position. Now, conversely, the block is moving as fast as it's ever going to move. So it has maximum kinetic energy when we have zero spring potential energy. Then as the block slides past the neutral position, we start stretching the spring. So the potential energy of the spring increases until we get to the point where the block stops. The force in the spring is enough to stop the block, so you have zero kinetic energy and max potential energy again. So that's characteristic curves. Now, the insight you need to have on this, and it's probably occurred to you already, is that the total energy is always the same, no matter where we are in this graph. And I drew it as best as I could, but it was freehand, so give me a break. But if you add together the potential energy plus the kinetic energy, you will always get a constant amount of energy, right? Well, a constant amount of energy which goes right across the top here. Where these two cross, there should be equal amounts of potential energy and kinetic energy. The way I have it drawn, looks like there's a little more potential energy, but like I say, I did the best I could. But if you add together the total energy at any point on this graph, it will always come out to a continuous amount of total energy, total mechanical energy in this system. So let's move on to the how this looks mathematically.